This is a grade 12 advanced functions lesson on graphing rational functions just in this form. Notice there's no power of 2 here, so these are just linear pieces, p at x over q at x. Let's do some review first. How do we find a vertical asymptote? So a vertical asymptote is found by looking for restrictions on the denominator. How do we find a horizontal asymptote? A horizontal asymptote, we look at the degree. So if the degree of the numerator is equal to the degree of the denominator, then we divide their leading coefficients, and that will tell us the equation of the horizontal asymptote, which is y equals, because it's horizontal. If the degree of the numerator is less than the degree of the denominator, then we have a horizontal asymptote right along the x-axis. How do we find the x-intercepts or the zeros? So you factor the numerator, or if it can't be factored, you're just finding the zeros of the numerator. That will tell you where the x-intercepts are. And how do we find a y-intercept? That's easy. We just sub in 0 for x. The last one, what about the oblique asymptote? That occurs if the degree of the numerator is greater than the degree of the denominator by 1. Then we're going to do division. The answer for that is the equation of the line of the oblique asymptote. Example 1. Match each equation with its graph. Okay, so these ones aren't too hard. You can kind of almost use trial and error to figure out which equation goes with which one, but we're going to put some reasons here just to kind of summarize. So if I look at the first equation right here, the first thing I see about this is it's got to have an asymptote at, it has a restriction on the denominator that x cannot equal 7. So that must mean, therefore, then we have a vertical asymptote at x equals 7. So that's enough, I think, really. There's only one on here that could be, and that would be b. So the other thing we could look at is the horizontal asymptote, just for some review here. The horizontal asymptote, because the degree of the numerator, so this is like x to the power of 0. The degree of the numerator is less than the degree of the denominator. We're going to have a horizontal asymptote at y equals 0. So that is b. Okay, now let's look at the second one. 4x plus 16 over x plus 4. We can do some factoring there. Change that to 4 times x plus 4 over x plus 4. And I see that looking at the restrictions on the denominator, x cannot equal -4. That means we're going to have a vertical asymptote at x equals -4. So there's none there. Vertical asymptote at x equals -4. So what did I do wrong? I don't think it's D. Well, let's look at other characteristics here. If I look at the numerator, that would give me a 0 at x equals -4, but I don't have that either. So what's the extra thing going on here in this question? Do you know what it is? Give you a second there to think about it. Hopefully you realize that these cancel. These factors are exactly the same and they cancel. So all we're really left with is 4. We're left with the equation, I'm just going to change g at x to y. We're left with the equation y equals 4, which is graph A. But the reason we have no vertical asymptote there is because the restriction canceled. This canceled out and this left us with a hole at x equals -4. So if we look up to the graph here, I'm circling the -4. When I look at x equals -4, my graph at that spot right here has a hole. So there's my horizontal line. This line's equation is y equals 4, but it's got a hole in it. So there was no vertical asymptote because it canceled out. So if you didn't factor, you wouldn't have seen that. You'd be looking for the vertical asymptote at -4, and you might have picked the wrong one. You might have thought, well, D looks like maybe it has a vertical asymptote there. But this one has no zeros because this canceled out here. So let me write no. We had no zeros, no x-intercepts. We had no vertical asymptote because of the canceling. So it's really important that you factor and then cancel so that you get the characteristics right. All right, let's move on to, so process of elimination down. We're down to 2 graphs that could match here. Hx, no factoring there. We can look at the degrees. The degree of the numerator is a 1. So this is a degree of 1. The degree of the denominator is a 1. When the degrees equal each other, we find our horizontal asymptote by dividing the leading coefficients. So our horizontal asymptote is going to be found by writing y equals, you have to write that for an asymptote. It's an equation of a line, it's not a number. So my leading coefficient of the numerator is a 1. My leading coefficient of the denominator is a 5. So I should have a horizontal asymptote at y equals 1/5. And when I look at the denominator, I should have a vertical asymptote. And the vertical asymptote, so to figure that out, I need this to equal 0. 5x minus 3 equals 0. Bring the 3 over. 5x equals 3, and we get x equals 3/5. So that would be this graph right here, graph C. It's hard to see, it's not really very well zoomed in, but we can see the vertical asymptote coming right down through here. All right, it's not right along it's got a y-intercept, so it's not coming along, it's not coming straight across. And the horizontal asymptote is just above 1 at 1/5 there, and that would be really hard for me to draw in, but that would be 1/5 right through there. Whoops. So that matches graph C. So obviously, which one could our last one be? I wonder. Well, let's just make sure we know the math behind the right answer here. Number 4, m at x. I can't factor anything. If I look at the denominator, x cannot equal -4. That means I'm going to have a vertical asymptote at x equals -4. So this is where I might have got, if I hadn't done the yellow work there correctly above for part number 2, I might have picked the wrong graph because if I hadn't canceled. But this is the one that has an vertical asymptote, not this one. It looked like we did, but we hadn't canceled yet, right? So now we have a vertical asymptote at -4. The degrees are the same. So our horizontal asymptote is going to be leading coefficient divided by leading coefficient, 3/1, which is 3. So horizontal asymptote at 3, that looks like that fits. Vertical asymptote at -4, there's -4. So that looks like that fits too. We could also go further and find x-intercepts and y-intercepts, but this answer is pretty clear. It's going to be D. Example 2, determine how the graph of f at x approaches its vertical and horizontal asymptotes. We haven't done this before. Approaches the asymptotes. How does it approach an asymptote? That's kind of a different style of question. So our function is in the form of, we have like a linear numerator and a linear denominator. We don't have anything too complicated there. So let's look first of all at what we can get out of the equation for the vertical and horizontal asymptotes. First of all, x cannot be -3. I get that from the denominator. That means we're going to have a vertical asymptote at x equals -3. So let's put that in there. The question's not telling us to graph it, but this would be too hard to explain to you without a graph. It makes it much easier. What else? So we need to know the horizontal asymptote. Where's the horizontal asymptote? Look at the degrees of the numerator and the denominator. The numerator and denominator have the same degree, so our horizontal asymptote is 2/1, which is 2. So there is our horizontal asymptote. Now we have some work to do. So that really was the easy part, figuring out where the asymptotes are, but now we have to talk about kind of the behavior. Right, let's talk about the vertical asymptote first. I'm just going to put an equation at the top of the vertical asymptote. The equation of it is x equals -3. So I want to know what's going on the right side and on the left side of that asymptote. The first thing, since x cannot equal -3, we know we have an asymptote there, but can x equal -3.00001? Yeah, it can. So we can't sub in a -3 into this equation because of the denominator, but we could go right beside it. So here's -3 on the axis, but I could go right beside it and sub in -3.001, or on the other side, -2.99999. So let's start with looking on the right-hand side of -3. So I'll write this down here. So we're talking about the vertical asymptote here. We're going to look on the right, look to the right of the asymptote. So to the right of it, the kind of notation we'll see for that is we're going to look to the right of -3. So that would be -3. And I'm going to put a little plus sign like a superscript up here. And that just means it's on the right. So just on the positive side of -3. And then I'm going to look, so obviously if I look to the left, it will be a negative up there. And we're going to look at very, very small intervals. So another way I'm going to write that is as x approaches -3 from the right, as x approaches -3 from the right. So for example, a number like -2.9999, however many nines you want to do there. So for this kind of experiment here, what I want you to do is put that -2.99, use it in your calculator, and I want you to sub it into the function here. So everywhere there's an x, I want you to put a -2.9999, put in a bunch of nines, and here as well, -2.99. So pause it and do that, and then we'll take a look at what your calculator is showing you. Okay, you did that, I hope, and you put it in your calculator, and what you're getting, depending on how many decimal places you put in, the more you put in, the better. The closer to -3 you get, the better. You're going to be getting, your answer is going to be negative, but it's going to be big. Maybe it's going to be about 7,000 or something, or sorry, it should be way more than that. You should be getting like 700,000 or negative. More numbers you put in, the bigger number you're going to get. So let's say you're getting -20,000. We're all going to have different answers depending on what we sub in. So you're going to get, the point is that it's negative, because look at this asymptote here. The number I'm getting when I sub in just on the right of -3, just on the right side, I'm getting a really big negative number. So maybe you got -20,000. That's way down here. See my mouse going way down, way down, way down, way down. So the closer we get to this asymptote from this side, so the closer I get, the closer number I sub in to the asymptote, as close as I can get to that asymptote, the closer I get, the more negative my answer is, the bigger it is. That means I know then that my graph's shape is my graph is going to be coming down like this. I know on that side of the asymptote, it's got to be coming down in that direction. So that's the behavior on the right side of the asymptote. Now let's do the same thing. So if you're not getting it, you don't understand where that came from, it's okay. We're going to try again. We're going to this time look to the left. We're going to look to the left of our asymptote. Look to the left of our asymptote is at x equals -3. So just to the left of it, we write that as x. We want to get an x value that's approaching -3, but on the left of it, on the negative side of it. So a number that's just on the left would be -3.0000, however many zeros you want to put in, and a 1. That's really, really close to -3, but it's just beside the asymptote. So it's just, if I just put with my marker here, here's -3, right? I'm trying to get right in close to -3. I'm trying to get really, really close to -3, but on the left side. So So I'm trying to get really close there. So because I can't put in a -3 into the formula, but I can sub in this number that's really close to -3. So I want you to try that. So you sub that into your calculator. You pick this number really, really close to -3. We're approaching -3 from the left, and you should be getting a really big positive value. So it depends, again, on how many decimal places you put in, how close to -3 you're getting. But in any case, the important part is it's positive and that it's big. So that tells me that my graph on the left side of the asymptote, I'm going to draw in up here. I know that it's going up. Whoops, shouldn't be curving that way. I know that it's going up on the left side of the asymptote like that. So what I've got now are two parts of the graph based on the behavior surrounding the asymptotes. So I'm just going to write a little bit more up here. See where I wrote look to the right, -3. So as x approaches -3 from the right, our function, I'll put it in orange, our function or our y's approached -infinity. So end behavior. On the left side, as x approached -3 from the left, I'll just write y as time instead of f at x, just to show you it can be, we're talking about both things. Our y values approach, remember on your calculator there, you got a really big number and it was positive infinity. So that is it's the end behavior of the asymptote. The end behavior of the vertical asymptote is what we just found there. So now let's talk about the horizontal asymptote. Horizontal asymptote. HA for horizontal asymptote. So our horizontal asymptote, we want to look at the end behavior of the horizontal asymptote. So that means this one's a little bit easier because the horizontal asymptote, there's one end over here and there's one end over here of the horizontal asymptote. The vertical asymptote had one end at the top and one end at the bottom. But here, all I need to do, if I want to know the end behavior of my graph, I'm going to sub in a big number, like 20, but really it'd be better if I subbed in, when I would do this with my calculator, I just hit 9 a bunch of times, but you can put in whatever you want. So you sub in a big number with your calculator. You sub in a large number for x into the function, and this number, for example, here, what have I got? How many 9s have I got there? Is it 999,999? Sub that in to your calculator or any big number, and you're going to get a number really, really close to 2. Because look at our asymptote here. I'm going to label it. Our asymptote equation is y equals 2. So I'm going to, the bigger a number I sub in, so I'm subbing in really big numbers from down here, like bigger than 20. I'm going to just keep finding a really big number, subbing in a really large number on this side here. And I'm basically either going to land above the asymptote or below the asymptote. So look at your number on your calculator. It should be really, really close to 2. As a matter of fact, it should be just below 2, 1.999999, depending on what you subbed in. So I'll just put that here. This is 1.9. This is approximate, right? But depending on what number you subbed in, that's approximately. So that means, so end behavior, as x approaches infinity, our y value is approaching 2, but from below. So how do you think I write 2 from below? Yes, you got it. I know you're all thinking it. It's a little minus sign right there. So my y is approaching 2 from below. So I'm going to erase all this red stuff I put on the graph. And I'm going to go back to orange, and I'm going to put a little end behavior piece here. I'm coming up underneath. I'm underneath the asymptote, and I'm going in this direction here. Oops, I need an arrow there on the end. So now let's look at the other side. I'm going to go back to red again. So I'm going to now look at this side here. So way over here, I want to sub in, my graph only goes to -14, but I'm going to sub in a really big negative number, like -9,999. I say 9,000. Or as many 9s as you want. Just remember to, if you're subbing in, to actually use this, if you count 7 9s on the bottom, 7 9s each time, keep it even there. So you sub a big number in, and then over here I'm going to write as x approaches negative infinity. So this time you're subbing in a really big negative number, which is really a small number. We're going to sub in as x equals negative infinity. You should find, when you do that, your answer is approaching 2. So I could say y ref at x there. It's approaching 2, but it's approaching 2 from above 2. You're getting really, really close to 2, but you're like 2.00001. So we're just above 2, so I'm going to put, yes, a little plus sign here to show I'm just above 2. Now I'm going to switch to my kind of yellowy color, orange color, and draw an arrow just above here, like this. See, the question didn't tell me to graph it. I don't need to graph it, but I think it's really helpful to be able to see it on a graph. So look at your arrows now. Again, we don't have to graph the question, but looking at the arrows, I can see that these two are going to connect like this, and these two are going to connect like this. And I could find y-intercepts and x-intercepts, and I know how to do all of that from previous lessons. I can do all that. I'm not focusing on that right now. The question didn't even ask me to graph it, but it asked about the behavior. So this, writing it out like this, is the way you write the behavior at the end behavior of the asymptotes. So you're kind of used to this infinity stuff, but you haven't really talked about this notation before. So that's how we talk about what's happening at the end of the asymptotes. And again, you have all kinds of characteristics. You know how to find intercepts and other values like that, and you could do all that. I'm just going to do a quick rough sketch in with the graph here. I'm not even going to find the asymptotes, and I'm just going to kind of connect my curves here like this, and on the other side. So again, I know there are obviously intercepts, x-intercepts and y-intercepts. I'm not calculating them. The question didn't ask me to graph it, but that would be the graph would look like. All of your graphs that have the format of today's lesson that was in the title for today's lesson, they're like this one that we're doing right now. There's no power of 2 or anything like that. We always have the two asymptotes, a vertical and horizontal, and our graph occupies diagonal quadrants. You just have to figure out where it's going to go. So let's go on to our next example. Example 3. State the equation of a rational function in this is what we're doing today, in this form. It has to meet these conditions and sketch the graph. So this is kind of a puzzle here. I've got all these pieces of the puzzle, and I have to come up with an equation and a graph from that. So all of this stuff is here. We've got a vertical asymptote at x equals x equals 3 over 4. We've got a horizontal asymptote at negative 5 over 4. So let me just throw those on there. There's my vertical asymptote at 3/4, and there's my horizontal at negative 5 over 4. So we've taken care of these two pieces now. But remember, we're not just graphing it, we are also going to come up with an equation. So actually, let's put the graph to the side for now, and let's focus on an equation. That's the more complicated part. So the equation, what should we do first here? Let's talk about the function, the setup itself. Because the degree of the numerator and the degree of the denominator the form we were given, they are equal to each other. It means we're going to have a horizontal asymptote at a over c. Follow me on that? Because when the degrees are equal to each other, we take leading coefficient, dividing by leading coefficient. So I know I'm going to have, I'm going to write this up here beside it, I know I'm going to have a horizontal asymptote at, so my horizontal asymptote is going to be at y equals, leading coefficient is going to be whatever a is, over c. So I'm going to have a leading coefficient there. But I have that clue over in the bullets. This bullet right here tells me I have a horizontal asymptote at negative 5 over 4. So that could be that A is 5 and C is 4. We would have to figure out which one is negative, but there could also be some factoring in there. So we have a few other clues we still have to figure out. Let's start with our vertical asymptote. I'm going to use a bunch of different colors here to try to keep things straight for you. So let's start with the vertical asymptote, the first piece. We already drew it, but what does this tell us about an equation, a vertical asymptote? Now, does it tell us about the numerator or the denominator? It tells us about the denominator. It's telling us that the denominator cannot equal 3 over 4. That's what the vertical asymptote is saying. So let's kind of reverse engineer this thing here. So I'm going to do the opposite operations. I'm going to multiply both sides by 4. So if I multiply this by 4, I get 4x cannot equal 3. Bring the 3 over, I get 4x minus 3 cannot equal 0. So there's my denominator. So I know I have a denominator of, so I don't know my numerator yet, but my denominator is 4x minus 3. And that fits with the asymptote clue that we talked about already, but we'll come back to that in a bit. So that's what we got out of our first clue. Our second one is that there are no holes. So no holes means nothing cancels. So I shouldn't be seeing a 4x minus 3 in the numerator because this tells me that nothing's going to cancel. So that's what that one tells us. Y-intercept at 2/3. Okay, let's go to blue here. Y-intercept at 2/3 means f at 0 has to equal 2/3. That's a y-intercept of 2/3. So if I go up to the original format, I've got f, I'll put it right. Okay, we've got f at x equals ax plus b over cx plus d. I'm going to put a 0 in there for those x's. F at 0 is going to equal a times 0 plus b over, that's crowded, sorry, c times 0 plus d. So that leaves us with b over d. So f at 0 is 2/3, and f at 0 is also b over d. So where am I going with this? Do you see where I'm going with this? Let me go back to this pointer here. F at 0 is 2/3. That was this. They gave it to us. F at 0 is 2/3. We also know by subbing in 0 up here, all these cancel out. F at 0 is also b over d. That means, okay, if we put that together, that means, now we've got some, we could have negatives in here. 2 negatives make a positive, so we could have that, but b over d's got to equal 2/3. So now they could both be negative, or they could both be positive, or we could also have multiples of them. B could be 4 and d could be 6, right? We could, because 4 over 6 is also 2/3. So, but it's still very helpful with what we've got, especially when we take a look at this piece right here. Look at the denominators, they both have that 3 in it. So some of you now hopefully are ready to, you have the equation, you've got it, right? You've got it figured out. Let's put what we've got together here. We've got our, let's look at our horizontal asymptote again. We've got a horizontal asymptote at -5/4. So I'm going to write this down below because it's getting, I'm going to take this down here. It's getting a little bit crowded here. What we've got is f at x equals something over 4x minus 3. Now if our b over d is, let me change this to ax plus b. We know from way up here, I'm circling the 2/3, we know that our d is 3, but we've got a -3 down here in our question. That means both of these are going to have to be a negative in order to get a positive 2/3 for our y-intercept. So what I can add into my equation here is ax minus 2 over 4x minus 3. That's going to give me my y-intercept of 2/3. Now all I have left to do is the a value. So this is why we're talking about the horizontal asymptote right now. The horizontal asymptote is -5/4. And looking up to the top right of your screen, remember we already talked about the horizontal asymptote is a/c. And if that's -5/4, where am I going to put the negative? That's the only thing I have to think about right now. It's going to have to go in the numerator, the negative, because if I look at my denominator, it's already done for me because I got that from the, I already got the denominator from the vertical asymptote here. So my numerator, my a value is a -5. -5x minus 2 over 4x minus 3. So let's see if that's right. We have some more clues that we haven't talked about here, and they're going to go into the graph. They're going to help us with the graphing. So let's put everything on that we've got so far. We've got the asymptotes on there already. We've got a y-intercept of 2/3. So 0 2/3 is, that's kind of hard to draw here. Maybe about there. Oops, it's a big dot. Okay. We've got the asymptotes on there, no holes. So looking at the second last bullet, it's increasing when x is between -infinity and 3/4. It's increasing. Doesn't mean positive. Increasing means going up. That's what increasing means. So from when x is -infinity, that's way over here. When x is -infinity up until 3/4, that's my asymptote. It's increasing. So that's telling me my graph must be coming up, increasing, and then it's going to go right along the asymptote here. So increasing means the graph is going up. It doesn't mean it's positive. It doesn't mean you're going to keep it above the x-axis. That's what positive means. It means above the x-axis. Increasing means going up. So we're going to run along the asymptote here, and up we go. If we look at our equation, what is the x-intercept going to be? So the x-intercept comes from the numerator. So I'm going to solve my numerator. -5x minus 2 equals 0. That's -5x equals 2. X equals -2/5. There's my x-intercept. So let's put that on. That's going to give us another clue as well. -2/5, that's pretty small. Right about there. Okay, so I'm going to now draw my curve, and I'm along the asymptote, getting a little higher, and then hitting these two dots, and then running along my vertical asymptote here. Whoops, curved in there. That's really wavy, and it's not supposed to be. I have this tablet here that's not being helpful right now. It shouldn't be wavy like that. There's that piece. Now looking at the very last clue, this function is negative. Negative means below the x-axis. That's what negative means. Increasing just means going up. Those are opposite, not opposite, they're completely different terms. Increasing goes with decreasing, negative and positive go together. So negative means it's below the x-axis, but that doesn't mean it's going down. Negative doesn't mean it's going down. Negative just means it's below the x-axis. So it's below the x-axis here from -infinity to -2/5, which is what you can see. I've already done that, right? Because we found out the x-intercept down here, which meant this is all negative, right up to bang, right up to that -2/5. This is all negative. This is all below the x-axis. Perfect. It also is negative from 3/4 to infinity. So that means this whole side here, when I start to draw this piece in, it has to all be negative. So it's going to be all in this section right here. Now it is possible to cross the x-axis a little bit and come back, but not for these types. These aren't going to cross. So I'm just going to do a complete sketch here. I'm not going to sub in any values and let's say, oh, what's x, what's f of 2? Let's get a coordinate. I could do that, but I'm just going to keep on moving a little faster here. There's my second piece. I know it has to be diagonally opposite the first piece. So that is a little bit more of a complicated question, but if you just take each clue one step at a time, it will give you a piece of the puzzle. Example 4, this is our last one. Sketch a possible graph of f at x. Consider all characteristics. All right, you guys have a huge toolkit of characteristics now. This one is not, this one's more complicated than everything else we've done today because of the power of 2, but we're going to put all of our skills to use here to come up with a possible graph. So remember, the first thing we do is we factor. There's a greatest common factor in the numerator right there. So I factored that out. Now I have a trinomial. Does the trinomial factor, sum and product, something have a product of -15 and a sum of 2? Yes. That factors to x minus 3 and x plus 5 with our common factor out in front of that too. Okay, it's all factored. Now we can start getting into some characteristics. What have we got? Well, x can't be 6, so we have a vertical asymptote at x equals 6. So, oh, I haven't put a scale on there. Let me draw, I'm going to count by ones on my x-axis, but just that. That's all I'm doing because I don't know my y-axis scale yet, but let me put my x-axis on. All right, so we've got that. We're going to talk about the degrees last, so that's the hardest part. So let's keep going with other characteristics that we can get from this. Here, we've got the denominator. What else have we got? Nothing canceled. So there's no holes. Don't go canceling crazy and say, well, I'm going to cancel that x with that x, and then that 3 with that 6, and I'm going to get a half. No way. Binomials must match binomials exactly. X minus 3 can only be canceled with x minus 3. Don't go crazy canceling stuff that can't be canceled. What else? What other characteristics have we got? The numerator gives us the zeros, remember? So we have x, we have a 0 from here at 3 and a 0 from here at -5. So we can put those on the graph. All right, so there's my x-intercepts. What else do we know? Y-intercept is f at 0 is 10. Okay, that's the first thing I have on the y-axis now. So I'm going to have to start thinking about a scale for my y-axis. I certainly want to get on that y-intercept of 10 on there. But before I do that, let's talk about the degrees. Look at the degree of the numerator, that's a 2. Look at the degree of the denominator, which is a 1. So the numerator degree is greater than the denominator degree by 1. We're going to have an oblique asymptote. We're going to have to divide. And remember the remainder. When x is huge, because we're talking about infinity today, right? Really big, big numbers. When x is huge, the remainder is so close to 0, it becomes insignificant. So when we're talking about end behavior of an oblique asymptote, it ends up just being the quotient part, regardless of the remainder. The value of the remainder, that's the remainder divided by our original function here, dividend, will always approach the value of 0. So don't worry if your remainder is 72 or 3, because we're talking about end behavior. When x is huge, that becomes insignificant. So that's an aside. Don't worry about that. Okay. Back to this degree stuff here, we're going to have to divide. So let's set up some division. What do you want to do, synthetic division or long division? I think everyone is voting for long division. Okay, let's do long division here. Any 0 placeholders needed? No. 8x minus 60, dividing that by x minus 6. So remember, our first step is the first term divided by the first term. That gives me a 4x. So it's 4x squared minus 24x. And subtract. We're left with 32x. Bring down the negative 60. Divide that in and we get a 32. Multiply it back, 32x minus 192. Subtract, again, we're going to have a remainder, who cares? We didn't expect it to go in evenly. If it did go in evenly, then we would have had some canceling happening way back at the beginning, so we weren't expecting that to happen. So now we have to graph that. we're going to graph the, let me just put y equals here. So I'm going to put a y equals just up at the top here. This is the equation of our oblique asymptote. That's our oblique asymptote. We have to graph that. Because of that 32, now I can see that I'm having big y values. So now I'm going to come up with a scale for my y-axis. We talked about graphing straight lines using y equals mx plus b, using the slope and y-intercept. Let's try another way we learned how to graph in grade 9 or grade 10 also is to use the x and y intercepts to graph. So we'll graph that one this way. I want to use my x and y intercepts to graph. So my y-intercept of that line is going to be 32. I get that by, sorry, I should write that down. I subbed in x equals 0. Or you look at your b value. This is your y-intercept right here, always. To get the x-intercept, I'm going to sub in, I'm going to do the opposite. I'm going to sub in y equals 0. So I put a 0 here, equals 4x plus 32. Bring the 32 over, and we get -8. There's our x-intercept is a -8. Now that's the x-intercept of my oblique asymptote, not the function f at x. This is just the oblique asymptote I'm talking about right here. So for my oblique asymptote, it has an x-intercept of -8. So I'm going to just put a kind of an x there on the -8. It's got an x-intercept there, and it's going to have a y-intercept of 32. So I'm going to count by tens, and I'm going to put a scale on my y-axis right now. Okay, I probably could have gotten away with counting by 5s instead of 10s, but that's all right. So my y-intercept is at a 32. So let's just say that's about there. I'm going to put an x there. Just using x's just so I remember to connect those dots. I already have some other dots on my graph from x-intercepts and things. Those aren't part of my oblique asymptote. So I'm going to get my ruler and I'm going to connect those two x's with a straight line. So I'm going to try to. Okay, I know that doesn't look good, but you have no idea how long it takes me to draw those lines, and it's not even going through 32, I don't think, but that's technology for you. Okay, so now we are going to, we still have to sketch the graph. We've got our asymptotes in there. We've got our oblique asymptote and our vertical. Remember, when you have an oblique asymptote, you will not have a horizontal. It's one or the other. It's either all the way flat or tilted up like this one. So we've got one more thing we're going to talk about, which we've been learning today, and that's about the behavior around the asymptotes. Now we can't talk about the end behavior of the oblique asymptote because it's not going in a straight line. Well, it's straight, but it's not going vertical or horizontal. I don't know what number to sub in on this end or on this end. So let's talk about the vertical asymptote. I want to find out on the right side of 6, where am I graphing up here on the right side of 6, or am I going to be down here on the right side of 6, and on the left side of 6, where am I going to be? So let me just write down the proper notation for this. For our asymptotes, as x approaches 6, let's do from the left first, from the left side. So you're going to sub in a number into your calculator, like, for example, 6 from the left would be 5.9999. You're going to do that. Make sure you use the same number of 9s each time that you sub in. So press pause, sub in 5.999, and you should get either a really big number, a really big positive number, or a really big negative number, which is a small negative number. So give that a shot. Press pause. Okay, and hopefully you found that your function f at x, or you can put y there, is going to approach -infinity. So I'm going to go over to my graph, and I know that on the left side of the asymptote, we're coming, whoops, down the other way, this way. Oh, I made a mess of that. All right, that's a bit better. So now we look on the other side of that vertical asymptote. as x approaches 6 on the right, so that would be about 6 point, however many zeros you want, just on the right of 6. So when we're just to the right of that asymptote, I'm going to put y this time. What is our y value approaching? What kind of a number are we getting there? Positive infinity or negative infinity? And take a second to sub that in. And you get positive infinity. So up to the graph on the right hand side of that asymptote now we are going to be coming up like this. So I also have a few intercepts. Remember we put those zeros on at 3 at -5. So I'm going to come around there. I also have a y-intercept at 10. I'm going to put that on. I haven't put that one on yet. Y-intercept at 10. So I've got 3 dots here in this kind of quadrant to hit. So I'll start at the y-intercept. I'm going to come around here, and then I'm just going to run alongside the asymptote. That's what would be happening there. From the y-intercept to the right, I curve around, hit the x-intercept, and then I'm going to connect up with my line there. Now the only clue I have right now about where else to draw my graph is that little arrow we got on the right hand side of our asymptote right here. That's my only other piece of information. So that's all I need to know right now for this stage of what we're learning. We're going to learn more later. So I'm going to just draw kind of a little curve shape in here that's going to, I could sub in a number if I wanted to sub in 8 just to see where it's going to be. But I'm doing a possible graph right now, so I'm just going to do a little curve like that in there. All right, lots of stuff in that lesson. Taking so much of what you already know, like the division and the factoring, and asymptotes and everything, putting it all together here to come up with, every time we learn something new, we get a better and better possible graph. We're getting closer and closer to being accurate. So that's the end of the lesson on graphs of rational functions.